We're continuing with section 16.3. We're exploring a little bit more the concept of path independence in relation with conservative fields. And also we're going to explore a little bit over the concept of having curl equal to 0 and conservative fields. So in here, the first thing that we learned just now was that if f is conservative, then f is path independent. And then it turns out that if f is path independent, on S open connected domain. So that's the side note. Then f is conservative. Two pieces to it. One way, f conservative, f is going to become path independent. Then you have to have a somewhat nice domain. And then if f is path independent, f is going to be conservative, or f is going to have a scalar potential, which means f is going to be conservative. So how does this work? If the f is path independent, then you can find from any point P to any point Q, you can find basically you fix your starting point P, and then for every point Q in the domain, you are going to be able to find a path from P to Q. Then if you do the line integral of that path, that gives you the potential function at point Q. So fix P. Again, potential functions can be different and a constant. So fixing P is not going to make a whole lot of difference. It's just going to make a difference in a constant. And then the potential function is going to be that line integral from P to whatever point you're evaluating the potential function at. And that's the beauty of it, basically. And so the theorem says a vector field F on an open connected domain D is path independent if and only if it is conservative. And we learn how to find if it's path independent. We learn the method of finding that potential function. Just fixing a P, and for every Q in the domain, you can find a value, and that value makes that potential function. So now we're discussing the relationship between conservative fields and simply connected domains, and when curl is equal to 0. So we know that the conservative field are irrotational. That is, the curl of the field is going to be 0 vector. And so question, is every irrotational vector field conservative? And the answer is requires us to define this notation of simply connected domain. So a connected domain is just when any 2 points can be connected within the domain, is simply connected if it has no holes. More precisely, every loop in D can be contracted to a point while staying in D. So if I look at this loop in D does not contract to a point, because I press it, make it smaller, and there is a hole in there, so I cannot contract it. But if I just take this piece and that piece is going to be simply connected, but the two of them together again are not going to be simply connected. And so basically there's no simply connected means no holes and no breakage and that sort of things for the region. So the theorem says let F be a vector field on a simply connected domain D. If curl of F is equal to 0 in D, then F is conservative. Again, both times going from F conservative, you didn't have to worry about the domain issues. You would just imply something else. But when you're trying to prove conservativeness, the domain comes in. So just curl being 0 is not enough for the field to be conservative, even though field being conservative, so F being conservative gives you that curl of F is 0. But curl of F equal to 0 does not imply F is conservative unless you have that F is defined in pretty much some hole-less, breakage-less domain. That's what it is basically. Example time. Is F of... So let's do an example, example 2, and this is related to conservative fields and simply connected domains. So the field is 3 plus 2xy and x squared minus 3x squared. And so what I need, again, up here, to make sure that field is conservative, we need two important sections. Curl of F has to be 0 and F has to be defined on a simply connected domain, or continuous on a simply connected domain. These are the elementary functions, both of them. So, and they are defined on the entire R2, both of them, and therefore the field is continuous over the entire R2, and the domain is R2. And so the part about simply connected domain is done because there's no hole or breakage in R2. Now the next part is to find the curl, and curl of F is equal to ijk, the partials, and then 3 plus 2xy, x squared minus 3y squared, and 0. And so what we learned is to find this, basically I have to cover this side and this side, and then I will get the partial respect to z of x squared minus 3y squared z, x, and y. This is going to be 0. So the first component is 0. And this is always the case when you have a two-dimensional vector field and you're finding a curl. Now, the next one is going to be basically, let's see, it covers J and the first row, and I get again with the first one I got a negative sign in here, and again I get partial of x with respect to z minus partial of x with respect to z, x of 0, and then plus partial of z with respect to partial respect to z of 3 plus 2xy. Again, what? This is going to be 0 because it's partial with respect to z. The only one that is not going to be 0 is the kth component. And the kth component is going to be the partial with respect to x of x squared minus 3y squared minus partial with respect to y of 3 plus 2x, y, and k. And this is going to be 2x, and this one is going to be minus 2x, k, which is 0 vector. And so the curl of f was a 0 vector. Again, I knew that the first and second component are going to be 0, but the third component I checked and it was 0. And therefore, and because the domain is everywhere, we have a conservative field. You can take this further, find its potential, and then use that to compute the rest of the material. And computing potential is just going to be basically integral of 3 plus 2xy. That's with respect to the x. And I get 3x plus x squared y plus whatever left over with respect to the other function of other variables. And then here I will get x squared minus 3y squared dy would be x squared y minus y to the third plus c with respect to this one c1, c2 function of x, and that's the reason I chose c1 and c2. Now, and what is in common? The common part is x squared y. What is not in common? This is 3x is not in common between the two of them, and over here negative y to the third is not in common. So this and that. But y to the third is a constant, so this could be that function, and 3x is a constant, so it could be that function. So the potential is going to be x squared y plus 3x minus y squared plus c. And that is the potential function for this conservative field.